So this ship right here weighs 2 pounds or 0.91 kilograms, and it's pulling on the ceiling hooks with a force of 8.9 newtons. And that means that the ceiling hooks are pulling on the ship with an equal but opposite force of 8.9 newtons. And if this ship were to fall, the force of gravity on it would be 9.1 newtons because it weighs 9.91 kilograms, and you times that by the gravity, which is negative 10 meters per second, and you get a force of 9.1 newtons. So I'm listening to music, and the TV sends an alternating current to the speaker, which vibrates the speaker cones, which vibrates the air around it, sending the sound wave through the air, vibrating all the particles so I can hear it. If I turn down the volume, the amplitude of the sound wave gets smaller. And if I turn up the volume, the amplitude of the sound wave gets bigger. Now, he's about to change the pitch of his voice. When he does that, it means that the sound wave will have a shorter wavelength and a higher frequency. And he just did it right there. And that's how sound works. So shout out to Veronica for ripping out all her subs and helping me put them in my car. So we got the power line to the amp right here. Here's the battery, so 12 volts from the battery to this line. It goes through a fuse so that you don't blow the speakers or the cable, and it runs through the cabin, through the firewall, through this hole right there, comes underneath the carpet all the way back to the rear seats, and it comes underneath this carpet and plastic piece, and it exits right here and then just slips its way into the trunk. So then it comes out under this sub box right here to the amp, and the amp is then grounded to the body of the car right here, and that's how you get a loop. The actual loop, it goes through the body of the car back to the battery, and then the resistance on this amp here is 22.18 kilo ohms, and so I'll use that in a calculation to find how much amperage would be flowing to the amp. So here's my equation for current running through the system of the subwoofers. We got current equals volts over ohms. There is 12 volts from the battery and 22,190 ohms. That was converted from kilo ohms. And then our resistance is going to be 0.0054 amps. So here we have meatballs and boiling water, and the stove is transferring heat to the pot, which is transferring heat to the water, and then the hot molecules in the water go to the top and the cold molecules sink to the bottom, and it's just a cycle. And then when it's boiling, it reaches the thermal equilibrium, and then the heat is transferred to steam, and then that would become a phase change. And then over here, it's the same thing. The burner is heating up the pan, which is then heating up the meat, and then they release steam because of the oil in the meat, and that's a transfer of heat to the air around it. And that's pretty much how thermodynamics works. Alright, so I couldn't get an exact video of this because I was driving, but I was at a red light on my way home from work, and I went from 0 to 60 miles per hour in 5.3 seconds, which was calculated on the stopwatch of my phone. And so 60 miles per hour is 26.82 meters per second. And then I stayed at a constant 60 miles an hour for the next 5 seconds. So a total of 10 seconds of time. And my acceleration was 26.82 divided by 5.3, which is 5.06 meters per second. So I would start up here at 5, and we'd go over to 5 seconds. And then my acceleration would drop down to 0 all the way for the rest of the trip, because I was then going 60 miles per hour. So pretty easy acceleration graph. Okay, so I actually messed up on the velocity graph. I didn't do it correctly. But here's my position and velocity graph. So because my acceleration was 5 meters per second, and in the single direction, my velocity would actually go to 5 at 5 seconds, just above 5.3 seconds, and my velocity would be constant until the end, 10 seconds. And my position graph would be like this till 5 seconds, because I'm increasing with the acceleration, and then it would slowly ramp off into kind of this weird diagonal as I remain a constant speed. So I believe this is probably not correct, but that's okay. Alright, so I chose to do buoyancy instead of light, and I have this glass cup that would simulate a beer pong cup, as if I was playing beer pong. I'm not right now, unfortunately. I just got off work, but so I have this ping pong ball here, and you can see that the water level is equal to the skull right here. And if I drop this in, it goes up just below the pink letters. So the buoyancy force of this ping pong ball would be equal to the weight of water displaced, which would be that little millimeter in between the top of the skull and just below the pink letters. This isn't a very great one just because the ping pong ball is so light. So let's say I was, I don't know, working, I had a glass of water next to me, and I dropped my screwdriver in there. You can see that the water displaced is now just above the pink letters, maybe a little bit more. And so the buoyancy force on this is not big enough to make the screwdriver float. However, the buoyancy force would be equal to the weight of water from the skull up here. So if I were to pour all this water out and pour just that amount of water in and weigh it minus the cup, that would be equal to my buoyancy force. So I talked about sound waves a little bit on my sound part, but sound waves need a medium to travel through because they vibrate particles, which vibrate other particles and then travel that way. Whereas an electromagnetic wave does not need a medium to travel. So that is why we can get visible light from the sun, because of this wave, it's able to travel through space and pass through the medium of the atmosphere. However, it does leave behind some X-rays and gamma rays, which are harmful radiation waves. And so that just kind of leaves us with the visible light here on Earth. And that's how we get light from the sun.